Hello students, once again all of you are welcome to my MRS math class. In the first lecture we have discussed about the basic concepts of differential equations, right? And here in this lecture I am going to talk about first order first degree equations, right? How we can get the solutions of first order first degree equations. Okay students, so basically it is very difficult to find the solution of the first order differential equations, in the sense that there is no formula for finding this type of equations, but however some standard types of first order differential equations of first degree are available for which we can get the solutions. So many methods are there. So in this lecture we will discuss about some methods. Okay students, so one important thing I must say here, that if you forgot or you are weak in integration, then you must revisit the topic of integration. That means you should have a good hand in integration, otherwise you cannot understand this lecture. Okay students, so here I will discuss about the technique, the first technique, that is your variable separable method. Okay students, variable separable method. Okay, so what it represents, from the name itself it is clear that something we have to separate the variables, right? That means here I can write the first order differential equation, that is dy by dx equal to f of xy. So this is a first order and first degree differential equations of the function x and y, where x and y are interlinked with each other. Okay students, so this equation I can write as some functions of x, that is your you can write m of x dx equal to n of y dy. So we can write in this way. That means some functions of x along with dx we are writing in one side, and some functions of y along with dy we are writing some another place. Okay, so what we will do next, we will integrate in both the sides to find the solution. This is very easy, but we must have a good hand in integration. Okay students, so some functions will be in this way, that is some functions n of y, okay, with some functions p of x you can say, okay, dy equal to some functions m of x, okay, and some functions q of y here dx. So this type of equations will be there, where functions of x and y will be mixed in one side and similarly in the other side. So what we will do, we will do that this n of y and this q of y we will take to this side. Okay students, and dy is equal to your m of x, right, by p of x dx. Okay students, we just separated out the y terms along with dy and the x terms along with dx to different side. Okay, then our duty is to do integration both the sides. Okay, then some constant, some integration constant we will get, and that will be our final solution. But also another thing, that this dy, okay, and this dx should be in the numerator part, that you should keep in mind. Okay students, so why we are, you can ask me that why I am doing integration after separating the variables, why not directly I am doing here. Okay, if in this way also we can I can do integration and I can get the result. But why I am doing this, separating the variables first, and we are doing. So I will explain it with one examples. Okay, students. Okay, students. So let us verify this method by taking one example. Okay, students. So let the first order and first degree differential equation, that is dy by dx sin 2x equal to y cos 2x. Okay, students. So here, what is our first job? That is separation of variables, right? So you can take this y to this side with respect to the side of dy, right? Equal to cos 2x, right, by sin 2x into dx. So very easily we just separated out the variables, right? X term, this is completely x term with respect to along with dx one side, and this y term along with dy to another side, and this dy and dx is in the numerator part, right? So our first step is successfully completed, right? So here, whatever the question I asked in that time, that why we are separating out the variables and doing integration, why not in the first step, right? So if you will do without separating the variables, right? So if you will take this dx to that side, and we will do the integration without separating the variables. So what will happen, right? See this, when we are doing integration with respect to dx, then this y will be treated as a constant, and directly we will take this y to outside, but it is not possible because I am repeating that this x and y are dependent on each other, so we cannot do that way, right? So we just separated the variables. Now we can do the integration both sides, right? So you know how to do integration. This dy by y will be your log y, right? And this side it will be cot 2x, right? Cot x integration is ln sin x, right? So this will be log of sin 2x, right? Log of sin 2x by 2, right? Plus some log c, that is integration constant, right? Then applying the log property, that will be 2 log y, then 2 will be go to the power of y, that is y square, and here log sin 2x, here 2 log c, another constant, so log sin 2x log c, and that will be your log of sin 2x into c, and both side log it will cancel. So finally we will get sin 2x, right, into c, correct? So if you will take the root over, then y into sin 2x into c. So this is the final solution curve for the differential equation, this. Okay, and how we did it by using the method of variable separable, and hence the result. Okay, students. So let us take another interesting example to verify this variable separable method, to understand variable separable. Okay, so the differential equation is x dy by dx equal to root over of 1 minus y square. So this is a first order and first degree differential equation which we are going to solve using the variable separable method. So how we will separate these variables? That is dy by root over of 1 minus y square equal to dx by x, correct? So next what we will do, we will integrate both the sides, correct? So this will be your sine of sine inverse y equal to your log x plus c, correct? So y will be sine of log x plus c, right? So this is the infinite family of curves for the differential equation this. Okay students, so here you can see while separating these variables, we have divided x root over of 1 minus y square, right? So here we can assume that y not equal to 1, right? Because in this case, denominator case, 1 minus y square is there, so we can assume that y not equal to 1, right? So this is our general solution for this differential equation. But here you can see y equal to e1 is a solution for the differential equation, but this one we cannot get from the general solution, right? Because we are assuming y not equal to 1. So this y equal to 1 is a singular solution for the differential equation. Okay. Now we will see another type of first order differential equation, that is your homogeneous equations. Okay students, so before that we should know that what is a homogeneous function. Okay, homogeneous function. Okay, so write down the definition. Okay, a function f of x comma y is said to be homogeneous of degree n if f of tx comma ty equal to t to the power n f of x comma y. Okay, so what is this t? T, where t is independent of x and y and t belongs to R. Okay students, so a function f of x is said to be homogeneous of degree n if f of tx comma ty equal to t to the power n into f of xy. So take an example and we will try to understand. Okay, so x square plus xy, this is our f of xy, x square plus xy, this is our function of x comma y. So we will write in terms of f of tx ty. So what it will be? It will be our t square x square, correct? And this will be our plus tx into ty, correct? So here you can take common t square and you can write x square plus xy, correct? So that will be our t square into f of x comma y, correct? So we are getting in this way. Here n is equal to 2, so this is a function of degree 2. This is a homogeneous function of degree 2. You can write, you can say, so many examples are there, like you can take sine of x by y, anything, right? Which are the examples of homogeneous function. Clear students? Now we will go to the homogeneous equation. Okay, so write down the definition. Okay, so a differential equation, write down a differential equation, that is m of x comma y dx plus n of x comma y dy equal to 0 is said to be homogeneous equation, okay, if both m of xy and n of xy are homogeneous functions of important thing, that is same degree. Okay students, so this equation 1, you can say this equation, right, this is a differential equation, right, it's said to be homogeneous if this m of xy and n of xy are homogeneous function of same degree. Okay, so you can take examples, right, that is x square plus xy dx plus your y dy, you can write equal to 0. This is a homogeneous differential equation, right? So this type of equation, how you will solve? By using variable separable method. So this m of x comma y dx plus n of x comma y dy equal to 0, this we can write as, take to that side, what you will get, dy by dx, right, equal to minus of m of x comma y over n of x comma y, right, this way you will get, right, and if this one you will take some function f of xy. Okay, so what we are going to do here, now we know that homogeneous differential equations can be reduced to a simpler form by applying some transformation, that is y equal to vx. Okay, so both sides doing differentiation, we will get dy by dx equal to v plus x dv by dx, correct? So this one will apply it here, right? So what you will get, v plus x dv by dx equal to minus of m of x comma vx by n of x comma vx, correct, equal to f of x vx, right? So you can write f of v, correct? So by separating these variables, what you will get, dv by f of v minus v equal to dx by x, correct? So now we separated the variables. Now we can solve by using the separable variable methods, correct? So this one we will understand by taking one example. Okay students? Friends, now we will take the homogeneous differential equation and we will solve it by using variable separable method. Okay students? So here you can see that we have taken an example, that is this function is homogeneous and this function is also homogeneous. So this equation is homogeneous equation. Now what we will do, we will find out dy by dx, correct? Right? So if we will find dy by dx, then this will be our minus of x square minus 2y square over xy, correct? So what the transformation I said to use, that is y equal to v of x, right? So your dy by dx will be v plus x dv by dx, correct? This transformation we will use it here. So what you will get then? This side will be v plus x dv by dx, correct? And this side it will be minus of x square minus 2v square x square over x into vx, correct? So x square in the numerator part, if it will take common, and denominator part there is also x square, so it will cancel. So finally you will get v plus x dv by dx equal to your 2v square. This minus, if it will go inside, then you will get 2v square minus 1 by v, correct students? Now we will separate out the x term to one side and y term to another side. If this v, it will go to that side, what you will get? This x dv by dx, it will be your 2v square by v minus v, that is minus v square, so you will get v square minus 1 by v, correct students? Now if you will separate out, then this will be your v over v square minus 1 dv, and this will be your dx by x, correct students? Now we will integrate both the sides, okay? So if you will integrate both the sides, what you will get? This if you will multiply 2 here, then in the denominator 2, then you will get 1 by 2, right? Log of v square minus 1, is it visible? Yes, equal to log of x plus log of c, correct? So this 1 by 2, it will be go to the power of v square minus 1, that is root over of v square minus 1, right? So log both side if you will cancel, then it will be your c of x, correct? So v square minus 1 will be your c of x square. So what is our v? V is equal to y by x, correct? So this one now we will substitute here, that is y square minus x square minus 1, that is your c of x square, correct? So y square minus x square will be c of x fourth, correct? So y square will be cx fourth plus x square, right? And y will be your root over of this cx fourth plus x square, right? X square, correct student? So this is the solution card for the differential equation, for the homogeneous differential equation, this, and we used the separable variable